climate change. It's right there, undeniably shaping our world. And the search for ways to tackle it is pushing researchers towards some truly ambitious, even radical ideas.
Absolutely. And one concept you hear tossed around is geoengineering, or maybe climate intervention. This idea of deliberately trying to manipulate Earth's systems on a large scale to counteract warming.
Right, and within that whole space, a really prominent idea researchers are exploring is called solar radiation management, or SRM.
Yeah, SRM. The core idea there is pretty straightforward, conceptually at least. Reflect a tiny fraction of incoming sunlight back into space before it gets a chance to warm the planet.
Deflect some sun.
Yeah.
Simple enough, right? And the approach that gets, well, maybe the most attention within SRM is stratospheric aerosol injection, SAI.
SAI. Putting tiny particles way up high into the stratosphere specifically to scatter that sunlight.
And the inspiration, it kind of comes from nature, doesn't it? Like big volcanic eruptions.
Exactly. Think Mount Pinatubo in the Philippines back in the early 90s. It blasted a huge amount of material way up into the stratosphere, and it actually caused a temporary but measurable global cooling effect.
Okay, so there's a natural precedent.
Right. And historically, the materials talked about most were sulfates, the kind volcanoes produce, because we know they reflect sunlight.
There's always a but, isn't there?
Well, yeah. Intentionally putting sulfates up there, it comes with some potentially significant downsides researchers worry about.
Like what?
Things like harming the ozone layer through chemical reactions, driving other kinds of what they call heterogeneous reactions. That's chemistry happening on the particle surfaces, not just in the air. And also the potential for acid fallout when the particles eventually come down.
Okay, yeah, those sound like serious concerns.
They are. And that's a big reason why the search is on for alternative materials. Could we do this reflection job without those specific problems?
Which brings us neatly to the really fascinating idea in the research paper you brought us for this deep dive. Instead of just reflective particles, what if you could use particles that do two things? Dual function particles.
Right. Made of materials that could potentially both reflect sunlight and maybe capture carbon dioxide directly out of the air up there in the stratosphere itself.
Wow, okay. Two birds, one stone kind of idea.
A really creative concept, trying to maximize the benefit. And the material this specific paper looks at for this dual job is called zeolites.
Zeolites. Okay, so our mission today in this deep dive is to really unpack this research paper. You shared the source, and we're going to guide you through what it found, looking specifically at the feasibility, whether this zeolite idea actually holds water, according to the study.
Exactly. And just as a heads up, the paper really digs into evaluating this dual function concept, and, well, it reaches a pretty clear conclusion about whether it could work as hoped in that stratospheric environment. Maybe not what you'd initially expect.
Right, sounds intriguing. Let's get into it. So we're talking geoengineering, specifically SRM, trying to bounce sunlight away. And SAI, stratospheric aerosol injection, is the main concept for how you might do that using these tiny particles high up.
Precisely. And that Pinatubo eruption back in 91, it's like the textbook natural example of SAI. It put huge amounts of sulfur dioxide into the stratosphere, which turned into sulfate aerosols.
And those particles just hung around?
They did, for a couple of years. And they reflected enough sunlight to cause that temporary dip in global average temperatures. It basically proved the mechanism can work, at least physically.
So it gives us a starting point, a demonstrated effect, but like you said, doing it deliberately with sulfates, that raises big questions about unintended side effects.
Serious questions, yes. So the scientific community is looking hard for materials that could maybe give us that same cooling effect. The technical term is radiative-forcing, but without the known downsides of sulfates, especially the ozone issue and those surface reactions.
Which is where the idea of multifunctional materials comes in. Can one particle do more?
Exactly. Can it be more than just a tiny mirror?
And that brings us back to zeolites, the proposed dual-function star of this paper. What exactly are zeolites? I feel like I've heard the name, maybe in filters or something.
That's a really good connection, actually. Zeolites are basically crystalline aluminosilicates. You can think of them as minerals, but with this really unique atomic structure. It creates a whole network of microscopic pores and channels.
Like tiny sponges.
Yeah, like tiny, highly organized sponges or cages, right down at the molecular level. Very specific structures.
Okay, microsponges made of minerals. And the idea for their dual function, it comes from properties we already know they have, right? Down here on Earth.
Yes, exactly. They're really well known, as you hinted, for their gas adsorption capabilities. They can be exceptional at it.
Adsorption meaning grabbing onto gas molecules.
Right, sticking them to their surface.
Yeah.
Because of their specific pore sizes and this huge internal surface area they have, plus a particular knack for interacting with molecules like KO, they're incredibly effective. We use them already in things like separating KOs from industrial emissions, from flue gases, and even in some direct air capture or DAC systems.
Okay, so we know they can grab coheros from the air, at least under normal conditions. What about the second function, the reflection?
Well, they also inherently reflect some light, particularly in the shortwave part of the spectrum, which is where most of the sun's energy comes in. So the thinking was maybe they could scatter sunlight effectively too.
And the study focused on one specific type, ZSM-5.
Yes, ZSM-5. They picked that one because existing research suggests it has a good combination of relevant properties.
Such as?
Well, it's known to be pretty selective for grabbing coheros compared to other gases. It doesn't have a huge affinity for water vapor, which is good because there isn't much water up there, but you don't want it interfering. And it seems to hold up well under temperature changes and UV radiation exposure.
Both pretty important for surviving in the stratosphere, I imagine.
Absolutely critical. You need something stable in that environment.
Okay, so based on what we know from ground-level uses, ZSM-5 sounds like a pretty smart candidate for this dual-function role. But here's the twist, right? The stratosphere is just completely different from down here.
That is the absolute crux of the issue. The stratosphere, especially up around 20 kilometers where you'd likely do SAI, it's an incredibly extreme place compared to the surface. Totally different conditions.
How different are we talking? Can you give us a feel for it?
Drastically different. The air pressure is incredibly low. Think below 55 hectopascals. That's less than 5% of the pressure at sea level. Like less than 5/100ths of an atmosphere.
Wow.
And critically, the amount of coeuro within that already thin air, the partial pressure of coeuro, is minuscule. Less than 0.04 kilopascals. And it's unbelievably cold. We're talking 190 to 220 Kelvin, which translates to roughly minus 83 down to minus 53 degrees Celsius.
Minus 83 C. Okay. So extremely thin, extremely cold air, and hardly any coheros molecules floating around relative to the total pressure. How on earth would that affect a material that's supposed to absorb gas?
Profoundly. Those conditions fundamentally change how materials behave, especially for gas absorption. Zeolite absorption, how well it grabs onto gases, is highly dependent on pressure.
Makes sense. More pressure, more molecules bumping into the surface.
Exactly. At those incredibly low partial pressures of coeuro you find in the stratosphere, the driving force, basically, the rate at which coeuro's molecules encounter and stick to the zeolite surface, it just plummets dramatically. The material's actual capacity to hold coeuros becomes totally different.
It sounds like trying to fill a bucket from a dripping tap versus a fire hose.
That's a pretty good analogy, yeah. The concentration, the availability of the molecules you're trying to catch matters immensely.
So the study didn't just look at the material in isolation. They also thought about, okay, how would you actually deliver this stuff? They designed a conceptual delivery system.
They did. They designed a conceptual pod using OpenSCAD, that's a type of 3D modeling software, to sort of map out what it might look like.
And what was the pod itself made of in their concept?
They proposed using carbon fiber reinforced polymer, CFRP. You see that a lot in aerospace because it's got a fantastic strength-to-weight ratio, really important when you're setting stuff high up, and it can handle those extreme stratospheric temperatures, both hot from sun and cold in shadow.
Okay, strong and light. What did the pod design look like?
It was imagined as a streamlined cylinder shape, to minimize drag going up. Inside, it had different sections. A chamber for the zeolite payload itself, a bay for sensors to monitor things like altitude, temperature, pressure, and then a nozzle system for actually dispersing the particles.
And how did they plan to stop the zeolite powder from just clumping up inside?
Good question. They included radial baffles like internal walls or dividers within the payload chamber, specifically to help prevent the fine particles from agglomerating before release. And the release itself was through dispersal ports that were electromechanically actuated.
Meaning they could control them precisely.
Exactly. Allows for controlled opening and closing, timing the release.
And how would this whole pod get up to 20 kilometers?
The idea was to use existing high-altitude tech. So either large high-altitude balloons, the kind science has already used for atmospheric research, or maybe high-flying drones, UAVs, capable of reaching that kind of altitude.
And they mapped out the whole mission sequence too, right? Like from the ground up.
Yeah, they simulated a plausible operational sequence. Starts with selecting and preparing the ZSM-5 particles, getting them to the right size, around 5 microns, they suggested, which affects how long they stay up.
Then loading the pod.
Right. Load the payload, seal it up, run checks on the sensors, then launch, maybe via balloon, and it passively ascends, logging data all the way. Once it hits the target altitude, it checks the conditions. Are they right for dispersal?
And if they are?
Then the autonomous dispersal kicks in. Those actuated ports open, maybe in a specific timed sequence, possibly even adjusting based on real-time wind data to try and shape the particle cloud. And all the while, it's still monitoring and logging data. Then maybe you'd even try to recover the pod structure afterwards.
That's a pretty detailed concept. Did the paper give specs for this pod? Size? Weight?
It did, based on their modeling. They envisioned a pod about 1.2 meters long, maybe 0.35 meters in diameter. It was designed to carry roughly 8 kilograms of the zeolite payload. The structure itself would weigh about 2.5 kilograms.
And how much area could one pod cover?
Their simulation estimated that a single release could disperse particles over an area of roughly 10 square kilometers.
Okay, 10 square kilometers per 8 kilo payload. So we've got the material, ZSM-5 zeolite, promising on paper. We've got a conceptual delivery system. Now, the million-dollar question. When they modeled how these zeolites would actually perform under those brutal stratospheric conditions, what did the results show? Did that dual function promise hold up?
Okay, yeah, this is really the core finding of this study. And for that dual function idea, the results were, well, pretty challenging. They ran the numbers specifically for that stratospheric environment.
Let's take the cryo capture first. Given those incredibly low pressures you described, what happened?
They used standard modeling for gas absorption Langmuir isotherms, but adapted for those specific stratospheric conditions. And the results were stark. Basically, the zeolite's capacity to actually take up curioros is, for all practical purposes, negligible at those pressures.
Negligible? You mean like just a bit less effective, or?
No, I mean really negligible. The study quantifies it. The performance for curioros absorption drops by over 99.97% compared to what you'd expect in, say, a ground-based direct air capture system.
Over 99.97% worse?
Yes. The model capacity up there falls to below 0.001 millimoles per gram of zeolite. It's essentially doing nothing in terms of curioros capture in that environment.
Wow. Okay, so that's pretty definitive. The curio capture function just doesn't work in the stratosphere because of the physics of low pressure.
Based on this modeling, yes. The driving force, the partial pressure of curioros, is simply far too low for the zeolite adsorption mechanism to be effective. The molecules just aren't there in enough concentration to stick significantly.
Okay. That side of the dual function is out. What about the other half? The reflecting sunlight part, the SRM? Did that look more promising?
Well, they looked at that too. They modeled the scale you would need. How big an area of these reflective particles would you need to create in the stratosphere to actually get a measurable global cooling effect? They used a modest target, like cooling the planet by about 0.1 Kelvin.
Okay, 1/10 of a degree Celsius cooling. What kind of reflective area did the modeling say you'd need for that?
To get even that small cooling effect, the modeling indicated you'd need an unrealistically enormous reflective area, something approaching 1 million square kilometers.
1 million square kilometers? Didn't the pod disperse over like 10 square kilometers?
Exactly. The required scale for even a small global cooling effect is something like 5 or 6 orders of magnitude larger than what one conceptual pod could disperse. It just highlights this immense logistical and scaling challenge. You'd need an unbelievable number of deployments.
So let's put those two pieces together. The FEO capture is negligible. The scale needed for reflection is gigantic. What's the bottom line from this research paper about using these dual-function zeolites, ZSM-5, in the stratosphere?
The study's conclusion is really unambiguous. Based on their findings, this specific dual-function concept using ZSM-5 for both significant coadjo capture and significant SRM in the stratosphere is simply infeasible.
Infeasible? Why?
Because the geoengineering capture essentially vanishes due to the low pressure, and the scale required for the SRM part is orders of magnitude beyond what seems practically deployable with this kind of approach. The physics and the logistics just don't line up for this particular idea in this environment.
So it sounds like it's basically a disproof of concept. Like the science shows why this specific, initially appealing idea just won't work when you look at the real-world conditions.
That's exactly how you could frame it, and the study itself points out the real value in that kind of finding. It's a crucial piece of the scientific process.
So, isn't a negative result kind of disappointing?
Not at all, scientifically. This is a great example of constraint-based design, understanding how the environment itself imposes fundamental limits. Getting a clear disproof of concept like this is incredibly valuable because it helps researchers avoid going down blind alleys. It stops potentially huge investments of time and money into pathways that just aren't viable based on fundamental principles.
Right. Better to find out now through modeling than later through expensive failures.
Precisely. So while the core idea was creative, and maybe the delivery pod design has some merit for other things, the fundamental physics of adsorption at low pressure and the sheer scale needed for reflection mean this specific zeolite approach just isn't the answer for stratospheric dual-function intervention.
Okay. So what are the key takeaways or lessons learned that the study highlights from doing this investigation?
Well, the big one is that any modeling for these high-altitude ideas must rigorously account for how material properties, especially things like absorption capacity, change with pressure. You absolutely cannot just take performance data from ground level and assume it applies up there.
Terrestrial assumptions just don't work.
Fundamentally flawed for gas adsorption in the stratosphere, yes. And the other big lesson is about scale.
That 1 million square kilometer number again?
Yeah. It really hammers home the immense challenge of albedo modification. If you want to reflect enough sunlight to make a global difference, the scale is just staggering. It's a completely different kind of problem than, say, localized cloud seeding.
So how do findings like this help shape the broader search for climate intervention strategies? Does it shut things down or redirect?
I think it redirects. It tells the research community, okay, this specific material, VSM5, for this dual purpose in this environment. It's probably not the way forward. It helps narrow the search space and focus efforts elsewhere.
Did the study suggest where those efforts might go? Did they propose future work building on this?
They did suggest several avenues. For one, more detailed modeling using computational fluid dynamics, CFD, to better understand how clouds of these particles would actually behave once released, how they spread, how fast they fall out, whether they clump together, things like that.
And engineering the delivery systems.
Yes, more detailed thermal and structural simulations for the pods or whatever delivery method you might use. Those are still relevant engineering challenges for any kind of stratospheric deployment.
What about looking for different materials? Did they suggest that?
Definitely. They mentioned exploring alternative sorbents materials that grab gases, maybe modifying zeolite surfaces somehow, or looking at entirely different classes of materials like metal organic frameworks, MOFs, which can sometimes be engineered for specific properties, maybe even low pressure performance.
There's another catch there, isn't there?
There is, a crucial one they point out. Any alternative material would still need extensive testing to see if it can actually survive in the stratosphere long term. How does it handle the intense UV radiation? How does it react with the ozone or other trace gases up there? Finding something that absorbs well at low pressure is only half the battle. Yeah. It also has to be stable and not cause new problems.
Right. You solve one problem, but maybe create another.
That's always the risk you have to evaluate. Another idea they floated was maybe decoupling the functions. Instead of trying to get one particle to do both jobs, maybe focus research purely on reflective-only materials, optimizing just for scattering sunlight effectively and safely. Or, conversely, maybe explore deploying sorbent materials in lower parts of the atmosphere, like the troposphere, where the pressures are much higher.
Though particles might fall out faster down there.
Generally, yes. Residence times are shorter, so trade-offs everywhere.
Okay, so bringing this deep dive into the paper to a close, the main message, based on the study you shared with us, seems to be this idea of using ZSM-5 zeolites for both chromatic capture and reflecting sunlight way up in the stratosphere, while innovative, ultimately runs into fundamental roadblocks.
That's the core conclusion, yes. The physics of gas adsorption just don't work well enough at those incredibly low stratospheric pressures for the COA part. And the sheer scale required for the reflection part makes it seem logistically infeasible with this method.
So, not a workable solution as proposed here.
Based on this study, no. But again, that's a valuable finding for the research field. Knowing what doesn't work and why it doesn't work is just as critical for making progress as finding things that do. It helps focus efforts more effectively.
What aspect of this really jumps out at you? For me, it's that almost 100% drop in capture performance just due to the pressure change. It really highlights how context, the specific environment, is everything.
That performance cliff is definitely striking. And building on that, maybe a final thought for you, the listener, as you encounter more research in this area. What does the sheer scale involved in some of these global geoengineering ideas, like needing 1 million square kilometers of reflective area, or the extreme sensitivity of these materials to environmental conditions like pressure, what does that tell us about the immense difficulty and perhaps the profound responsibility involved in any attempt to deliberately engineer the climate on a planetary scale?
It certainly underscores the complexity and the high stakes. Well, thank you for walking us through this fascinating and perhaps sobering research paper. It really highlights the detailed work involved in evaluating these big ideas. We hope this deep dive helps you better understand the science and the challenges in the field of climate intervention. Keep digging and keep asking those critical questions.